All right. Hi, and welcome to our 11:30 a.m. press conference explaining extreme events of 2016 from a climate perspective. Our speakers today are Jeff Rosenfeld from the American Meteorological Society, Stephanie Herring from NOAA National Centers for Environmental Information, Andrew King from the ARC Center of Excellence for Climate System Science, and Chris Funk from the U.S. Geological Survey and the University of California, Santa Barbara.
Well, hello, and thank you all for being here. I know it's a nice day outside. Not extreme, though, so it's okay to be inside for a little while. The American Meteorological Society is pleased to issue this 6th annual edition of Explaining Extreme Events from a Climate Perspective. Every year, this report fulfills the expectations that we have for it, except this year. For the extremes of 2016, the report made clear that exceptions have changed and expectations have changed. Here's the thing. For the first time, there was one, then two, ultimately 3 events that the authors examined that turned out to be quite literally beyond the usual expectations. These events were not just influenced by human-caused climate change. That's what most of the 27 papers found, and there are 21 different events that they covered. Instead, the evidence indicates that some of the events in 2016 could not have happened without climate change. And with that, the report suddenly went from fulfilling expectations to exceeding them, at least exceeding expectations sooner than a lot of people expected. Let me explain. The old saying is, climate is what you expect and weather is what you get. That means, unfortunately, nobody talks about climate. If climate is expected, then it is the assumption. And unfortunately, people don't talk about assumptions. We talk about weather because we live in weather. We live in droughts and hurricanes, heat waves, blizzards. The point of this report is to get climate into that conversation. How can we talk about climate when we're talking about weather? About 10 or 15 years ago, a way to do that emerged. Scientists developed tools to make the connection between human-caused climate change and the weather. This report was created to challenge those scientists to keep making those tools better and better. All the indications say the report is working. We ask our authors to explain the connection, or the lack of connection, to human-caused climate change. We ask that they do it concisely and relatively simply so that we can speak directly to people who are trying to plan for the next extremes. We ask the authors to be fast enough to be relevant to the weather conversation, to be rigorous enough so they meet our standards, and to survive peer review by independent experts who will continually ask, and do continually ask, for more and more from these authors. It's quite a bit of a process, and we try and compress it as much as possible. But the decision makers then will get real science, solid enough to build weather and climate resiliency. The science, on the other hand, gets insights that help improve modeling and prediction. And of course, the public gets a more informed conversation. The authors have been resourceful and the science has been growing. And from our point of view at AMS, we see a growing pool of reviewers who are holding these colleagues to exacting standards. A whole community seems to be emerging, people who are doing this kind of work and people who understand it and appreciate it, well beyond the 117 authors who are participating in this report this year. And that's what we expected. But if climate is what you expect, then weather somehow is not just what you get, it's what you don't expect. So in other words, we only pay attention to weather when it is extreme, when it is in fact unexpected, rare, or unusual. We are so accustomed to rarities that we expect the unexpected, the rampant wildfires, the Harveys, the Irmas, the Marias. So if unexpected is the norm for people, how will people notice when expectations have changed, like we're claiming this year? And we're saying, and have always said, that the odds changed. That's what we usually say, that the weather is now kind of juiced up to be different. But that still implies that the probabilities are more about different probabilities for the same old weather, not something new. With this report, though, some of these papers are actually saying something different. The conversation needs to change again. Maybe it should have changed years ago. We don't know that yet. But more than 100 papers have passed peer review for this report in the past, and not one of them have made this claim until now. Even beyond this report, such findings don't happen often. Because climate change was a necessary condition for some of the events in 2016, necessary in order for them to happen. This is what the science is saying. These are not just new odds, these are new weather extremes that were made possible by a new climate. They were impossible in the old climate. How's that for expectations? Climate change is what you expect. New weather is what you get. The authors and editors of the report will explain a little more thoroughly. Stephanie Hoerling, who's a lead editor and who's innovated this whole format, will be up next. Thank you.
Let's see if I can do this right. Thanks, Jeff. As you said, I'm Stephanie Hoerling from NOAA's National Centers for Environmental Information and the lead editor of this report. We've been publishing for 6 years now, and these are the covers of the various reports this year. Is the bottom right with the coral bleaching event. And we've now published over 131 papers, as Jeff mentioned, through a very rigorous peer review process. And this year, we have 27 reports covering 6 continents and 2 oceans. As Jeff mentioned, we actually started this report 6 years ago, not to prove that climate change was impacting weather, we actually already knew that, but really to try and advance the methodology and the science behind how we understand what the role of climate change is in these weather events and trying to disentangle that from natural variability. So what did we discover this year? Jeff already gave you a prelude to this, but we had 3 events that were determined by authors to not be possible without human influence. And this is, again, after 131 papers in 6 years, for us this was the first time we not only saw 1, but 3 events that fell into this category. This is actually evidence for new events, only possible because we have created a new climate. The global heat record was one, done by a group from NOAA, which was only possible due to substantial human-caused warming over the last 100 years. A group from Japan looked at record heat over Asia and also determined it would not have been possible without human-caused climate change. And a group of researchers from Alaska looked at the warming waters in the Bering Sea, which was part of the infamous blob, and found that it could not be explained without human-caused climate warming. So, what do these results really mean? And from a technical perspective, we have evidence now that climate change is pushing events beyond thresholds that could have been achieved with natural variability alone. Now, we've known for a very long time that climate change can alter the risk of some of these extremes, but previous events in this report always still fell within the realm of possibility of they could have happened without human-caused climate change. It's just that the risk or the likelihood or their intensity or frequency has changed. Other thing that's important to remember is these are not likely the first events of their kind. As I mentioned in the first slide, we do not have a very comprehensive or random sampling of events from around the world. We only looked at 27. And so statistically speaking, it's actually fairly unlikely that of those events that our authors looked at, 3 just happened to pick out the very first, or at least the first for this report, events that were not possible without climate change. So to say that these mark the fact that we've crossed a threshold. Of course, we need retrospective studies to look at this, but statistically speaking, we likely crossed that threshold already, and we're just finding evidence for it in this report. It's also important to remember that climate change does not act alone. It never has, and as far as we can tell, we're still not acting alone. Natural variability is still a player in all of these extreme events. The caveat here, of course, is that climate change may actually be altering what we think of as natural variability. El Nino is a great example. We actually have a paper this year in the report from a group at NOAA that looked at how climate change may be intensifying El Nino itself. A few global highlights from other aspects of the report where human-caused climate change was found to have an influence. All of the heat waves and heat events that were looked at were found to be made more intense by climate change, as well as the El Nino that I mentioned. Arctic warming most likely would not have been possible without climate change. They came very close to getting a result that it was not possible at all, but it was most likely. The other category of papers that were very exciting for me in this year's report was these papers that really tried to link the event itself to environmental impacts of the event. And so we had scientists looking at Great Barrier Reef bleaching in Australia and several papers that looked at marine ecosystem impacts in the Pacific. And they all found that due to increased thermal stress from human-caused warming of the ocean, environmental impacts were exacerbated. We also have a very nice perspectives piece from the NOAA National Marine Fisheries Chief Scientist and the director of our Physical Sciences Division at NOAA, talking about how this research is important for understanding these impacts and ultimately its application in aspects like marine fisheries management. We also had several papers looking at the drought in southern Africa and connecting this to food shortages. Actually, Chris was one of the authors on those papers. So again, this breadth of papers that's now scientists are moving beyond just looking at the event itself and trying to connect it to the consequences of the event, for me, is a very exciting evolution of this field. As always, we have papers that found no role for human-caused climate change. Of the 131 papers we've published over the past 6 years, about 65% have found a role for climate change, and 35% have not found that role for climate change. This year, 3 events that did not find a role included Snowstorm Jonas, the southeastern Australian rainfall, which was corroborated by 2 different papers, of which Andrew here was an author on one, and drought risk in northeast Brazil. That's a brief summary of what's in this year's report. I'm now going to hand it over to Andrew to talk a little bit more about the science of event attribution and how we actually get to these conclusions.
Okay. Thanks, Stephanie. So I'm just going to talk briefly about what we do when a climate change signal is not found. So with all of these events, there's both roles of natural variability and climate change. And particularly for smaller scale events, there's larger roles of natural variability relative to very large scale events, say the global heat. And that's why for these smaller scale events, it's often harder to extract the signal of climate change. And essentially that's the main objective of many of these studies, is to try and extract the signal of climate change. And with a few of these events, they were so extreme that they could not have occurred without climate change. So when we find that natural variability was, or rather we don't find a clear signal for climate change, this could be explained in a number of different ways. For example, that there might not have been a human influence on the event, that the factors that influence the event, obviously for different events there can be different factors. For example, El Nino was found in many of the studies to be a major driver of some of the events, but potentially for some events the particular factors that were studied were not influenced by human-caused climate change. And it's also possible that given the tools that we have today, we can't always find this climate change signal. So we have we do have lots of tools, lots of climate model simulations, good observational data in many regions of the world, but even within those tools, we can't always extract a signal. So I'm just going to talk about that a bit more, about just how we look at the different roles of human-caused climate change and natural climate variability. And as I was saying before, and Stephanie alluded to as well, many of the events this year had a very clear El Nino component. So 2015, 2016 was an El Nino, a very strong El Nino, by some measures, a record-breaking El Nino. And many of the events had an El Nino signal. And essentially, what we do with these studies, if we're looking for the role of human-caused climate change, is we often have model simulations representing the world of today. That's the world in red, the current world. And we also have model simulations that represent a world without climate change, so an alternative world where humans haven't emitted greenhouse gases or aerosols. And we can compare these two worlds and look to see if that extreme event occurs in those worlds. What was interesting in this report, of course, is that there were 3 events highlighted by Jeff and Stephanie where, in the natural case, there were no events like the event we saw in 2016. And we do much the same thing if we're, say, looking at the role of El Nino. We can use model simulations or subsets of model simulations where we only look at El Nino years and compare those with say La Nina years or all other ENSO states in the current climate, and we can then look at the role of that form of natural climate variability as well. And we can do this with other types of climate variability. For example, last year there were very warm Indian Ocean temperatures that were used in looked at in a few different studies and found to play a role in some extreme events. So all the events here have some natural component, and that tends to be what makes them extreme even in today's climate. So, for example, if we had a 25-degree day in New Orleans in December, that would be very warm for New Orleans, but only about 1 degree Celsius of that would be due to climate change. Part of that warmth is just due to the weather systems at the time, and basically the winds coming from the right direction to have that warmth. On the larger scales, the global scale, the variability plays less of a role. So for some events in this report, they would have been virtually impossible without climate change. And what that means is that even though natural variability might have enhanced that warmth, climate change has pushed it over the line, basically where we couldn't get that kind of event in a pre-industrial world. And just as an example of this, if we look at the global temperature series, at the end there we've got 2016, and the forecast for 2017 is the green bar. But you can see 2016 stands out way above the other years. And obviously part of that being a record is due to that El Nino last year. That made it a bit warmer, say, than 2015 or 2014. But if you go back to near the start of the series, there are no years anywhere near like 2016. And that's because climate change, human-caused climate change has warmed the planet, and we couldn't get years as warm as 2016 without human-caused climate change. There are a number of studies that have looked at the global temperatures like this, and for example, a study that I led a couple of years ago found that going back to 1998, all of the global temperature records we've seen since then could not have occurred without human-caused climate change. So if we look to the future, that kind of means as well that any future global temperatures, whether they're records or not, really have quite a clear climate change signal. We couldn't get years as warm as we've seen in the last decade or two, and we're going to see in the next few decades without climate change. But what's quite exciting about this report is that we're seeing in other regions of the world, like the Bering Sea, warm ocean temperatures, those temperatures being almost impossible without climate change. So what we're really seeing is that for areas of the world where there is very rapid warming, like the Arctic, or areas where the variability is very small, such as in the tropics or in the oceans, the ocean temperatures, we see a very, very clear human signal. And one key example of that is with the Great Barrier Reef bleaching event, which is included in this report. So I'm now going to hand over to Chris, who's going to talk more about the impacts of the impact studies on this report.
Great, thanks. So one of the things that came out in a lot of these studies, and it was really interesting to see this emerge, so it wasn't, by design, but a lot of these studies focused on marine waves. And marine heat waves alter the ocean's temperature, salinity, nutrient levels, and they can have billion-dollar impacts on fisheries and tourism. They can also have important secondary impacts, helping to produce droughts in places like California, South Africa, Thailand, India. So to help you guys to understand how these heat waves might play out, I created this animation that shows the fraction of attributable risk. So this is how likely we think that this event couldn't have happened without climate change. So, a number near 1 means that there was a very strong human-induced component to it. And so as we go month by month over the last couple of years, we see these heat waves move around and persist. And so that, there were just 3 studies that had, a 100% outcome where this event couldn't have happened without human-induced climate change. But there are a lot of other areas of the world that were probably suitable for that same kind of analysis. And in terms of thinking about impacts, climate change manifesting its way in terms of these sea surface temperatures is really important to understand, because they're going to have important consequences on our fisheries, on our marine resources, but they're also going to create secondary effects by altering weather systems. And that creates opportunities for prediction. So I work a lot with food security in the U.S. Agency for International Development. Here's a slide produced by the World Food Program, just calling out different crises related to the 2015-16 El Nino. And so this is one kind of impact. And we looked at about 11 million people who needed food aid in Ethiopia as a result of the El Nino-related drought. There was about $500 million in agricultural impacts in Thailand produced by the drought. In Southern Africa, we saw about 24 million people pushed near to the edge of famine, requiring humanitarian assistance. And to understand how that happens, you have to think about a poor household in a place like Malawi, where somebody will live off $60 a year. And they'll spend 60 to 70% of that income on food, and when there's a drought, you can see prices jump up by 50%, creating food access crises. So it's really important that a couple studies from this report, linked that drought and those food insecurity outcomes to climate change associated with the El Nino. And we also saw El Nino-related impacts in Haiti and Central America. But there's a silver lining to this story, which is that these kinds of marine heat waves, these really extreme sea surface temperature conditions, tend to be predicted really well by the current generation of climate models. So in the bottom left of this panel, you see North American multi-model ensemble of forecasts for December, January, February of 2015-16, made in August of 2015, so way in advance. And these extreme sea surface temperatures were really well predicted. So that creates opportunities for prediction. And I've shown here in the bottom right some climate scientists from Southern Africa that's their job. And these people will really be on the forefront in many ways of helping us adapt to climate change through improving our predictions. Another example drawn from work that I really was involved with involved what happened in 2017 after the El Nino. And the red line there shows West Pacific sea surface temperatures, and the blue line shows El Nino sea surface temperatures. So we had this almost unprecedented spike in El Nino sea surface temperatures, followed by an unprecedented spike in West Pacific sea surface temperatures, right? So the blob, there's a big blob in the East Pacific, followed by really dramatic warming in the West Pacific. And in part because of the work that we had done on previous extremes issues, analyzing the impacts of those really warm sea surface temperatures, we were able to issue some successful predictions for the drought in the fall of October, November, December 2016, in the spring of March, April, May 2017, which helped us get food aid to millions of people, particularly in Somalia, staving off what could have been another famine like we saw in 2011. So, these marine heat waves are out there. They're really becoming quite easy to detect from the natural background. They're persistent, and they may create opportunities for prediction. Thanks.
Thank you. We will now take questions from reporters who are in the audience. Can you please state your name and affiliation? Are there any questions?
Can someone, at Seth Borenstein, the Associated Press, can someone explain a little further the blob and how we know that is just, that it couldn't have happened without, I'm trying to find a good way to explain what the blob is, what it did, and why we know, it's easier to explain heat waves than that, why we know that's not possible in a pre-anthropogenic warming situation.
Let's see. Oh, it is on. Sorry, I wasn't sure. Actually, Seth, the methodologies and a lot of the approaches for the marine heat waves aren't extremely different from some of the heat wave components on land. So if I hope that maybe helps simplify things a little bit. They actually do use some of the same models. So as we all should know by now, hopefully, oceans are absorbing the vast majority of the temperature increases that have been caused by human-caused climate change. We haven't observed them, they're not being felt as strongly on land as they have been in the ocean. So it's not surprising, actually, that we would be seeing some of these events in the ocean, but they do use very similar methods and techniques. They use some of the same global models, and they compare a world in which the oceans were allowed to progress naturally, as Andrew mentioned, versus a world that we actually live in, where we have human-caused climate change. The other component of this, of course, is observations. And so one of the things that strengthens the amount of the confidence that we have in various results is the quality of the observations. And so this particular area within Alaska and off of the coast of California, there is a pretty strong observational network that's been operating for quite a while. And so the authors were able to go back, I believe, until the late 1800s, early 1900s with their observational network. So the results from that perspective are quite robust.
Just explaining in lay terms what the blob did.
What the blob did? Well, in terms of the event itself, I mean, it was anomalous ocean. It was a very high anomalous ocean warming that actually stretched from the Bering Sea, which is sort of the eastern side of Alaska, through the Gulf of Alaska, and down towards the coast where it meets up with Washington. And so that whole area, I don't know if we actually have a picture on a slide, but that whole area was quite warm. And then in terms of the impacts of the blob, they were, the fisheries impacts have been quite extensive. Actually, there's been recent reports that perhaps, for example, cod fishing catches may have to be reduced because of fish stock impacts. There's been massive die-off of birds that normally live along that area. There have been other environmental impacts in terms of some of the marine life they've been seeing off the coast of Alaska. So certainly within Alaska, it's something that's been in the news on a very regular basis because of the impacts. It's not just a warmer ocean. But I
guess, didn't it also affect the climate in California a bit? Or?
I'll let Chris speak to that one.
Sure. Yeah, so, well, I can't summarize. It's a pretty big group of literature, but there's been studies by people like Daniel Swain, linking the blob to the ridiculously resilient ridge, which being from California, I can speak to this experientially, that, that basically those really warm sea surface temperatures persisted for about 36 months or so, a long time, and the ridge sat above there, and it was this incredibly persistent atmospheric feature that pushed storms to the north and produced drought over California, and then also contributed to some really extreme winters in the eastern United States.
Are there any other questions from reporters in the room?
Hi, Robert McSweeney from Carbon Brief. The debate around climate change is often going on during these events, so the sooner that we get these sort of studies, the better. How do we balance the need for attribution studies in real time with the rigors of peer review?
Can I take a swing at that?
Yeah, go for it.
Well, I don't know if I'm speaking for all the panel, but I think one of the things to recognize, just looking at the kinds of studies that were in this issue, is that there are some things that are relatively easy to attribute in real time. So for example, it's pretty easy to make a map of sea surface temperatures and ask, is this the warmest it's ever been? Or to say, like the animation that I showed, which was just a map of these kind of attributable risk maps. That's pretty easy to do in an automated sense. So just like air temperatures, assessing whether air temperature is exceedingly unlikely or not given climate change. That's relatively straightforward. But then these kind of secondary influences, like for example, the influence of the blob on California, the influence of El Nino on Southern Africa, I don't think that that's probably going to be done in real time anytime soon.
Can I add something? Yeah. So I think there's also value in both approaches, and with rapid attribution analyses that are becoming more common now, and I've been involved in a few through the World Weather Attribution Project. They're typically associated with quite simple variables and events that we've already got kind of peer-reviewed literature which we can link to. What the value is in some of these reports in this BAMS issue is that they can basically dig deeper and look more extensively at the roles of both natural and human-caused climate influences, and also dig deeper into the impacts than would be possible in a rapid attribution study.
I would say that in a way the original intent of the report was to kind of demonstrate what was possible. So that's why the peer review is so important to this report. Now, we often are seeing techniques that have been tried out elsewhere but not quite as rapidly or combined with the kinds of impacts maybe we're trying to see how it works. So the papers are trying some new things, and at a certain point you say, okay, this is good enough. I think, and then if somebody has the computing resources to do it and the time, then maybe they can do it faster, and they will start doing it faster, but they probably won't until they see enough studies peer-reviewed that establish, hey, this works, before they should be. And you see that with weather forecasting. Certain techniques don't go in until they've been bandied about in the peer review, and then eventually you see it in the operational models later on. So that's kind of what the purpose of the report is. And even now, we've gotten to the point where we get enough submissions and want to focus that we don't. We kind of say no to reports, to studies where it's pretty obvious that this is well tested and we don't need any more of these types of papers. So the papers have evolved a little bit as we try and select for things that are a little bit new, that need to be tried out and need to be peer reviewed.
Hey, my name is Brian Resnick, and I write for Vox.com. I was wondering if you all, or a few of you, can help explain and describe some of the key caveats or limitations to attribution studies. I know, a lot of these are built on assumptions that you make of what the world would look like if there was no warming. Of course, those are always going to be assumptions, and we can't, make that as an experiment. But yeah, so when you say some events would not have happened without global warming, without human-induced climate change, it's pretty bold. I'm just wondering, like, if there's ways that we should be thinking through how you do these analyses, and maybe there's some limitations to those conclusions.
I can do a starter on that one. So every attribution analysis is built on really three fundamental components. One is the strength of the observational record. And so this is why it is incredibly important that we continue to invest in long-term monitoring of our Earth system, because extremes by nature are rare. And so by looking back over the observational record, that's really one of the fundamental ways in which we can have an understanding of, well, even what is the likelihood of this event in today's climate. And so that's certainly one component. The strength of the observational record does vary based on where you are on the planet. So, and that can be true because of just the instrumental record and satellite records, but also the paleoclimatological record as well. So that's one component. The other caveat, of course, is the models. and the quality and the ability of the models to replicate the event in question. I think it's really important to remember that not all extreme events are created equal. So when it comes to things like heat and ocean temperature, we have a lot of good evidence over a long period of time now that we've been running these models, that the models are quite good at capturing changes in temperature and changes in both the land and somewhat in the ocean. And that's, of course, there's some variations, obviously regionally, and I won't get into that level of detail, but overall, there's a lot of confidence in the models in that component. Now take something on the other extreme, something like a tornado, where we not only do we have a poor observational record, but the models, when it comes to, I mean, of 131 papers, we've never published a paper on tornadoes, and I don't expect to see one anytime soon, because the models simply can't capture that type of physical phenomenon, and there's very, very little confidence, and it would be hard to make a statement with any kind of certainty about tornado, a particular tornado event and climate change. And so that's two different ends of the spectrum. And the other events sort of fall somewhere in the middle, where you have, precipitation and drought. Again, the confidence that we have can vary on geography. So that's always one of the caveats. And then finally, not just the model's ability to replicate an event, but do we understand how climate change we expect climate change to change that event in the future? What's our understanding of the physical processes that drive that event and climate change's impact on those physical processes? And that varies by event type. And the National Academy of Sciences actually did a nice report where they looked at all the different event types and tried to assess of these three elements, which events we have that for, better or worse, and in terms of the strengths and weaknesses of our level of understanding for different event types. And that's the biggest, I think, caveat area that it cuts across all events and all attribution reports. And then within every individual report, we can go into the details, but I'd say that as a field, those are our three big sources.
I'd also add, I don't know if you had, Chris, did you want to add it? Okay. No, just to say, which we often say and may have already said, that it depends on the type of question, how you ask the question, what aspect of the extreme, and how you define the extreme as to how the result might come out. So you might get a different paper on the same thing, same event, but a slightly different question, might come up with some slightly different answers. Probably not radically different answers, but they're reconcilable, but the answer looks a little different. So that's another so-called caveat, I guess, you might see.
The only other thing I would say is you were kind of saying it's quite bold for scientists to make these very strong statements. In general, with these attribution studies, we're being very conservative with what we're saying. So the estimates we give are often quite conservative estimates, and we say that they're very likely greater than a certain, say 10-fold increase in likelihood. So for scientists to say that an event would be virtually impossible without climate change, they're very sure. I can say that.
I've never seen that language actually in a paper until now. In BAMS, where somebody says it's virtually certain that this was impossible without human-induced climate change. That virtually certain is almost certainly unheard of. but the way the study is constructed, it's very simple in some ways. These are very elegant. A lot of these are very elegant studies, so it's pretty hard to throw caveats in there when they don't seem to be there in the data.
And again, just to reinforce this idea of the convergence of evidence, right? I mean, you wouldn't want to just take one climate model and do one simulation and say, oh, that's the answer, right? Typically, these studies will do many different models. They'll rely heavily on the observational record. So you'll start with a situation where you have this sort of historical distribution and then a very warm event that's way over here. And then you'll do a lot more work and try to confirm, that big difference using climate models. And then you might come up and say that this was, almost impossible without human-induced climate change.
Right, and one other thing about there were some near misses, which I think Stephanie already alluded to, where one paper said, something like around 97%, human influence, and they're not among the three we're talking about. So there's some who really came close, and again, I hadn't seen that in previous reports until now. So it's just within the selection of our reports. It could happen elsewhere in other journals, but it's pretty rare, and it was quite striking this year to get 3 of them in one edition.
Are there any other questions on the chat? Go ahead.
We have a question from Chelsea Harvey, who is with the E&E News. And she wanted to ask, is it believed that the 3 papers in this report are the first ever to report events that were not possible without the influence of climate change, or just the first included in this report?
So I'll let Andrew talk about that one as well. But I would say that they're certainly the first in this report. And in terms of the literature overall, there have been other papers that have made sort of statements about whether something was virtually, you know, or almost impossible or things like that. And Andrew actually has been working on has worked on retrospective studies trying to look back in time at some of these global heat events. So I am not necessarily convinced these are the first ever in the literature, but these are some of the stronger statements that we have seen. And in terms of their FAR analysis and their ability to build on some of the methodology that we've been used and the robustness and the confidence that we have in their results, I think that they do stand out for that reason.
Yeah, I'll just add to that. Yeah, so there's been a few studies by myself, Michael Mann, and Stefan Ramstorff, who have looked at recent global temperature extremes. So like from the graph that I was showing. And basically, the last few global temperature records, there's peer-reviewed literature that says that they couldn't have occurred without human-caused climate change. But yeah, in terms of more regional scale events, so like the Bering Sea event, I personally haven't seen, I don't think I've seen any literature for regional scale events which has found, especially on such a small scale, that human-caused climate change is vital to that event occurring.
Are there any other questions from reporters in the room? Just reporters are able to ask questions. Are there any other reporters?
We have one over here.
Okay.
Hi, my name is Rosalind Driotta, and I'm with Climate Nexus. Given that this is such a bold moment, it seems, and given that scientists are so conservative, and Jeff, you mentioned that you think moving forward the conversation needs to change again. Well, given this, what would you like to see changing in the conversation?
Gosh, was that? I don't have to answer that, do I? Did anyone else? Since I kind of gave my answer in a way, I would say tipping my hat and saying that, you know, if scientists are saying that this is happening, that weather is different in this way we look at weather, in other words, we're seeing things that could not have happened without human-caused climate change, then that needs to be part of the discussion. We can no longer be shy about talking about the connection between human causes of climate change and weather. Certainly, most events, many events, you know, we're not going to make that connection directly. So, but it's part of the conversation, and it should be admitted, and it should be normal to talk about it that way. Because we have work to do, and so let's get on with it. That's my personal opinion. But I think the science is very clear that the conversation has to be framed a little differently. If anyone else wants to take that.
Yeah, I guess I'll jump into the fray a little bit. You know, I think, you know, if we're looking at these regions of extremely warm sea surface temperatures and thinking that you know, is going to happen more frequently, then, you know, I think we need to factor that into, you know, sustainable practices for our fisheries and think about how we're going to manage that. And then I think we also need to do a better job of integrating that into our weather prediction. You know, so for example, if we think about the blob, you know, the blob was sitting out there off the coast of North America for years. And you may remember back, but, you know, there was all that talk about the polar vortex, right? And so we had what was essentially a climate phenomenon, right, that the public didn't really pick up on as a persistent climate phenomenon, and it was really thought about as a weather event that lasted for 2 years, right? So I think culturally and scientifically, we need to expect the unexpected and learn how to deal with these really warm sea surface temperatures and their impacts. And I think the BAM's process of this issue is really actually a great tool for doing that.
Are there any other questions?
Barb Richmond from EOS at AGU. How far up the policy food chain have your results gone, and what's been the reaction?
I think, you know, thinking about all those fish and who had trouble with the blob, and the birds, and I just sort of feel like sort of picturing these reports swimming upstream, jumping their best to get somewhere. But I'm clearly the community is paying attention. So how far the policy chain, how far up the policy chain, I don't know. I hope it goes pretty far, though, because the thing is that this isn't just about the events where we know climate has caused something to be more extreme. In some cases, we have papers here that say human-caused climate change had a role in making something less severe. So you think about our society and how strapped we are for resources to deal with these incredibly big questions. It's nice to know not only what's going to get worse, but what's going to get a little less worse. Not all of it is bad news necessarily from a policy point of view. This is actually a big tool to make more effective policy decisions about how to use these resources. So I think actually there's a very good chance that this is going to help policymakers, especially at the regional level. We're talking about water management and drought management, electricity generation, which is so critically dependent on understanding climate, regional climate, infrastructure questions. This is a great tool to spread both good news and bad news.
Generally, on principle, don't answer questions with the word policy in them, but I'm going to switch it. I'll switch it around a little bit to me decision support, because I think one of the exciting things about this paper, about this report, was the number of papers that we had. And I said this in my talk, that linked to the environmental consequences. And we've actually seen some other papers in the past that link to things such as public health consequences. And so for me, that's really one of the exciting forefronts of attribution research, is to see these scientists working on these other issues. And what I think is particularly telling about a lot of these papers that are doing that is they're not just doing it within the attribution community themselves, but they're doing it across disciplines. So for example, the coral bleaching paper includes what we would consider a traditional climate attribution scientist working with someone in a marine biology department. Previous paper looking at health mortality from the European heat wave was a traditional climate change scientist working with public health departments in France and the UK. And that, I think, that kind of cross-disciplinary aspect, so not thinking about up the policy perhaps, but for me, thinking more about how do we start integrating the scientific understanding, and especially from the NOAA perspective, our understanding of environmental information, and link that with information and intelligence from other sectors and start drawing those connections to help other people make decision preparedness, resilience, things like that. And so for me, that's very exciting, and I think we're starting to see more of that within our community, is that cross-disciplinary conversation starting to happen.
And I think we are out of time. Thank you. That concludes our press conference. And our next press conference at 12:30 on the Mexico earthquakes.
Well, I mentioned it during my talk, so.